takes a second to spin this up. Okay. Okay, so thanks again for those of you who are joining us live. And today we have Vijay Thakkar, who is a grad student at Georgia Tech, and he's going to be talking to us about his ever popular HPC Industry Roundup. So lots of juicy bits to get into today. Take it away.
Everyone. Yeah, sorry, go ahead. My bad.
No, take it away, thanks.
Okay, awesome. Well, welcome everyone. It's been about a year since I presented one of these roundups. So although the last one is called second half of 19 and this one's first half of 20, it's more like this is a full year 2020 roundup rather than anything else. As always, there's a bit.ly link, HPC 1H20. I snagged a nice one this time around. So if you'd like to follow through, please go ahead. That'll give you to the Google Docs. I would prefer it if you would tag along at the same slide, because a lot of this stuff is not on the slides, and some of the stuff that's on the slides I'm not going to talk about. So yeah. All right. Anyway, so this time the roundup is a little different in that I'm going to start by some more disclaimers than I normally would. I am currently employed by a semiconductor company, so this is somewhat of a how to toe the company line. Everything that I'm going to talk about in this presentation does not, like, it's only my opinion, no one else's, so please don't sue me. Basically, that's the takeaway from this slide. I'm just required to have this slide everywhere. I also like to meme a lot, so please, if any of you are attending here are from a hardware company, I know people from Intel and AMD sometimes attend these. Don't take it the wrong way. This is just for humor. I'm just trying to make everyone laugh. So, you know, keep that in mind. I have also probably forgotten a lot of things, and I try to keep these as conversational as possible. So please feel free to interrupt or throw out any corrections or point out any new discussion points that you'd like. Otherwise, we're definitely not gonna use all of the time available. So please, if you have any discussion points, feel free to interrupt. Chat works too. I won't be looking at the chat, so maybe if someone can just shout out that there's a chat message, that'd be nice. But yeah, these are the 3 disclaimers I had. Cool. So the agenda for today is that we're going to talk about some of my own research over the last year or so at Georgia Tech. Then we're going to recap some of the stuff from 2019. Well, actually, that order is reversed. We're going to recap first and then go into the research. Then we're going to talk about the usual hardware stuff that we usually talk about. And then there's a lot more about systems this time around, because there's been a lot of HPC systems news. And then finally, we're going to end with silicon fabrication and some of the geopolitical news that we would sometimes cover. Normally that this would all be a SC meeting, but RIP SC, I guess it's fully virtual now, so that's something to note, especially for all the student cluster competition folks. And as we were having a talk about it earlier, cluster competition is also fully virtual on Azure Cloud now. So yeah, trends for 2020 are quarantine and cloud HPC. So there you go, they both gel. Okay, well, we're gonna first start with my personal research, which has, now that I have you hooked by the clickbait title, this is a little exaggerated. Beyond FMA is that's the clickbait part. The second part is not clickbait, which is that it's about accelerated SemiRing linear algebra. But to give you some context, let's go into the news that I covered last time within just 4 months. Within a 4-month time span, the major news that we covered were all of these. Now, I'm not going to read them out, but there were a lot of developments in the HPC universe in the second half of 2019 alone. So many new systems, hot chips happened, VLSI happened, SC19 happened. There were new exascale systems, and now Nirvana. I went into a deep dive of Nirvana stuff, of the slingshot. I had like 12 slides last time around. So many new ARM cores. So there's a lot of new news flooding around. And just like the hardware news industry, there's also a lot of new scientific papers, especially in the biomedical universe. There's a lot of stuff that is being researched continuously, and the rate of increase in papers is also exponential. So just like these roundups take up more and more of my effort to make every year, going through every single scientific paper also isn't an easy ordeal. Like, it takes a lot of time. If you just want to do a survey of each category of literature. So it becomes an increasingly hard problem to solve in terms of how do you find intersections between different research areas, and how do you construct a graph of knowledge that links different areas together. because sometimes it can be critical in repurposing existing research in different application domains that you otherwise wouldn't have before. So at the core, this is essentially a problem of how do you mine a continuous stream of data where the data itself is knowledge. Like how do you extract knowledge, like meta knowledge from the knowledge? And that is the overall problem statement that we were working on in collaboration with Oak Ridge National Labs for the last 5 months-ish. And the idea at the core is we can represent this scientific papers as a graph where each of the vertex of a graph is a concept, and the concepts are then connected with each other based on which papers are discussing what different topics. So you can kind of like take all of these research papers, take their abstract or their text body, and see which keywords they use, which are then your concepts. For example, in this case, as you can see on the left graph, hopefully the pointer shows up. For a currently relevant example, let's say there's a coronavirus infection, then there's different kinds of lipids that are on the cell virus body or the external shell of the virus or whatever. Those are the concepts, and then there's edges that are linking them if they are discussed in the same context together. Similar examples on the right side as well, where you have the different concepts of the drugs, diseases, and the proteins and stuff. So that's the first step. Now we have a problem formulation that we can critically think about. Now that we have this graph, can we just run Floyd Warshall on it? I mean, that's one of the first algorithms that we learn about when we do an algorithms class in computer science, which is that if you have a graph and you want to find some sort of meaningful, you want to reduce that to some sort of meaningfully usable representation, you can run all pairs shortest path on it to see which edges of which vertices are the closest with each other, which are even connected. So it can isolate which components are linked together and find the shortest path. Now that's what the research is about running all pairs shortest path at massive scale. I'm talking summit scale here, and I'll go into the performance numbers later. But at its core, all pairs shortest path can be formulated as a type of matrix product where instead of doing multiply and accumulate, you're replacing the multiply operation with add and add with the min operation. Essentially, and I'll go into one line of code later that will also show you this in example. The problem has the same formulation as a normal gem would, but with different operations applied to it. Now, these different class of operations are on a different technically calling them as a SemiRing. That's the technical term for them, which is that the semantics of the operation are somewhat related in that they share some common characteristics like group theory would. But the exact definition is different. Now, how do we implement this? So I just told you that this needs to run at a massive scale on Summit. And most of the computation power of any modern HPC system comes from the GPUs. So we need to write some sort of CUDA kernels to accelerate all pairs shortest path, which at the end of the day is a gem-like product. Now, we know that gem, which is just your normal matrix multiply and accumulate, maps really well to GPU hierarchies because it is very flops dense in that you're doing a lot of computation for a given byte of data. So the communication patterns and computation patterns as a whole remain the same between gem and any other semi-ring that we're trying to implement for, not just the min and the plus one, but any other. For example, Viterbi algorithm uses a different semi-ring than the min and the plus, but the semantics of the hierarchy remain the same. The compute is very different though at its core. And it does require some modifications in that you cannot initialize any state with zeros. For example, in a normal matrix multiply accumulate, you would just set the initial state to 0, the initial output matrix to 0, because it's something so natural that you don't even think about. You're just adding to a register anyway. You multiply two numbers and you add it to an accumulator register, and you keep doing that over and over again. Now, when you have a different semi-ring, our operation is no longer adding to that register, rather taking a min with it. So if you're trying to take a min, you cannot set it to 0. Otherwise, your entire output space would become just purely zeros because that's the minimum number you can represent. So instead, we have to set the identity element to infinity. So what I'm trying to make clear here is that even though Summit has V100 GPUs and GEM has a really nice library from NVIDIA called cuBLAS, cuBLAS is closed source. So we cannot easily modify cuBLAS ourselves to change this identity value. So you can't use off-the-shelf libraries to do this, which are traditionally shipped by vendors in a closed form. So closed form. We need something that is open source and modifiable for us, or you have to roll your own kernel. Now, if you have implemented something along the lines of cuBLAS, you would quickly realize that it's not really possible to implement something that is as performant and flexible as cuBLAS within a 3-month time span, especially with a small team of researchers, which is like 3 or 4 people at most. So what I ended up doing was take this NVIDIA open source library called Cutlass, which is originally intended for folks who are working on a new neural network research. And I modified that to include this new register initialization library. Now that was implementation-wise one of the hardest things to do, but performance-wise it has no cost whatsoever. The easiest thing for me to implement was the compute instructions, which you just simply don't take the multiply and you swap that out for the addition, and then you take the addition and you swap that out for a min. It's literally a 2-line change to the code base, so it was very easy for me to do. But I'll go into the performance implications of that later. And then lastly, BLAS 3 API also has something called the epilogue, where you can take the original input matrix, which is your output matrix, and then you can scale and then add the original matrix to it, which is called the epilogue. In our case, we also need to modify this epilogue to, rather than do just a simple scaling factor, we take the final minimum with it. So the epilogue also needs to change, which is a non-trivial modification, but has little to no performance consequence. In fact, it actually exposes a new way to optimize code, which is that if you're not taking the epilogue at all, you just have to simply do a store without any computation whatsoever. Now, this doesn't have a tangible effect on performance, but you can essentially eliminate the code from your kernel, which reduces code size, which is sometimes beneficial for iCache improvements on the GPU. So those are the 3 key modifications that are required. Now, let me go into what the performance looks like. So remember, the data movement is exactly the same as GEM. We're just loading data from global memory into shared memory. We're doing the tiled GEM loop on the shared memory by loading them into registers as accumulators. So the data movement looks exactly the same as GEM. So the only performance difference that can arise in this kernel is from that from the single line of code that we changed. Now, let me go into what actually changes in the kernel itself. The entire code base looks exactly the same, except for this one line, which is that instead of doing the multiply, hopefully you can see my pointer, this would be the normal GEM multiply and then accumulate. We're doing this min after taking the sum of the 2 input values. This is the only change in thousands and thousands of lines of code that change. But this is at the core of the register unrolled tile loop. So what we actually end up seeing in terms of observed performance is that this 1-line change causes the instructions within the GEM loop to change from 1 FMA over here. This would be the GEM case. We go from 1 FMA instruction to a series of 3 instructions, which first add, which is our perform the add, which is our add operation, and then do a predicate set and predicate based register write, which is how the Volta GPU handles conditional sets. So you see which, you set the predicate register based on which one is the actual minimum across the 32 SIMT lanes within a warp. And then you write that out to the registers where the output is. So we replace 1 FMA with 3 instructions. Now, since this is at the core of the unrolled loop, this is the operation that is performed n cubed times within the actual SemiRing matrix multiply. And if you look at the actual disassembly of the loop, we increase the instruction count by a factor of 2.56. And our throughput also reduces by a factor of 2.65. So what we can actually notice is that even though this is 2 flops per instruction, and this is also 2 flops overall, from the semantic point of view of the algorithm, which is that you just do a plus and a min, the performance is almost a third of what it would be. And the reason, so in that sense, it kind of breaks down a teraflop by 2 teraflop comparison. So although the teraflop numbers between the 2 kernels look wildly different, we are still utilizing most of the hardware. It's just that in the case of multiply and accumulate, there's a single instruction that heavy lifts everything in a fused manner, whereas we actually have to do one clock cycle issue for all the 3 instructions, one after the other. And that's the limiting factor that we have. It's not the compute hardware, it's rather how many instructions you can issue. And that is a design decision that the GPU makes, in that there is no fused min and then a sum operation. It's just not something that the hardware supports. So, oh, by the way, a small side effect of having 3 instructions instead of 1 is that in the fused multiply add, since the operation is fused together, you don't need an extra register as the temporary value. But in our case, we don't have a fused instruction, so we also almost double the register pressure of our kernel, which also halves the warp occupancy of each SM, because we simply don't have enough registers to keep that many warps in flight. So there's a lot of performance consequences of just simply changing one line of code. This also changes the tile sizes that are ideal for each kernel. So the tile size is half because the register count doubles. So you can only have half as many tiles in flight as you would otherwise. So what does this mean? What does this mean for us? Well, long story short, we ran this on Summit across the full system with almost the full system across 4,096 nodes. That's 24,000 GPUs, 24,576, I guess, to be technically correct. And that results in 136 teraflops at floating point 32 precision. So I believe this is the largest all pairs shortest path run recorded to date. I could be wrong, but I'm fairly sure we're right. This should be a paper at, well, this is going to be a paper at SC. So let me just tell you about it. It'll be called Scalable Knowledge Graph Analytics at 136 petaflops. Oh, by the way, I might have said teraflops earlier. I'm sorry. This is 136 petaflops. Oh, yeah, I did make a typo. I'm so sorry. Uh-oh.
Yeah, that's a big one.
Yeah, that's a pretty big typo.
Rich was just commenting in the chat. Yeah, okay. So a few orders of magnitude.
Let me we're into monkey patching here, you know. This is what agile development looks like. There we go. Sorry about that. Big typo there. So this results in 136 petaflops on Summit. Again, I'd like to emphasize the technical committee for this paper is about 6 people. So this is definitely, I was just working on the CUDA kernels. A lot of work has also been poured into the MPI optimizations and the communication avoiding part of the algorithm itself. So you should definitely check out the paper. The paper has a lot more detail about the application space, as well as what the important side parts of the medical literature mining are. There's also a lot of talk about the different algorithmic approaches we experimented with in terms of which types of broadcasts we used for MPI, and what sort of communication avoiding strategies that we used. I would also like to point out that this would not be possible without an open source library like Cutlass. So Go open source software, you know, this would be just almost impossible to do within a 3-month time period without Cutlass. So special thanks to NVIDIA for that. And of course, special thanks to Rich Woodhook. The circumstances for me being involved in this project are quite hilarious to me. So I would like to thank him for giving me the opportunity to work on something as crazy as this, you know, like, so there's that. Anyway, this is the first phase of my talk. If anyone has questions about this, I would encourage them to surface right now. Otherwise, the following phase of the talk is all about the other hardware stuff that we're going to cover. Questions? Anyone? Chat. Like, oh, small correction. Yeah. Yikes. Okay. Well, I guess if there's no questions, I'll go into the actual roundup part of the talk itself. And what better way to do that than to go for Ampere directly? I don't know how much you folks covered Ampere last time around. Elliot, do you know how in depth you went?
Not to the level you're going here. We covered it superficially.
Okay, so the natural next question that I got from a lot of people was, can we run this on A100? Can we run this on Tensor Cores? We're just doing GEM, right? Can we do Tensor Cores? And this is where I start complaining a little about NVIDIA. So please bear with me while I complain about NVIDIA. Anyway, let's just start with what A100 looks like and then take it from there. Again, NVIDIA's monoliths continue the series of monoliths. V100 was massive as well, and so is A100. A100 is even slightly larger, actually. which is 826 millimeters square on 7 nanometer, which I didn't think they would do. That's quite a large die. The TDP goes up by a very large factor, from 300 watts to 400 watts. That's a 33% increase right there. And of course, as one would expect, the memory amount also goes up. Nothing too surprising on that side. The actual surprising part for me was that they're using normal HBM2, not the FlashBolt version from Samsung. FlashBolt has a 33% higher bandwidth, which I feel they would need. Actually, if you compare the bandwidth per flop per byte ratio of A100, it doesn't look that much better than V100. It's actually kind of a disappointing improvement in terms of flop per byte. And I'll actually go into that in the system section of this talk as well. So I'm surprised they're not using FlashBolt, because if you remember, we covered FlashBolt almost 5-6 quarters ago. So I don't know what's up with that. Maybe Samsung is not able to fabricate it or something.
Other than the performance, are there downsides? Is cost
it's probably more
understood?
expensive.
Yeah.
It's probably way more expensive. And I don't think Samsung is able to manufacture it in the scale at which NVIDIA would need it, which is what I think is happening. But it's still somewhat disappointing because, yeah, again, as I said, it's flop per byte is actually worse compared to V100. So there's that. The interesting thing that you might have spotted is that it has half as many tensor cores as SM. Now, that may seem like a regression, but it's actually really clever. What they've done is V100 had 2 tensor cores per SM. They've fused both of them together to get double the reuse in terms of registers. So they reduce the pressure on the register bandwidth they would need. But at the same time, they've gone for a larger multiplication unit, a single one instead of 2, with the same number of elements in the gem tile. So it gives them double the reuse, reduces power, and it allows some free transistors that they get out of that with the node shrink, as well as the path optimizations, is that they can get FP64 matrix multiply accumulate in the same tile as well, which is super cool. So it was the next obvious change they would have done after V100, and that's what they've delivered. The L1 scratchpad size also goes up by 50%. I believe Volta was 96K, and this one's 192K. Again, pretty expected. N7 is really good with SRAM density, so it makes sense. Now, to get into the contentious part, the specs on the NVIDIA website are longer than you can put on a single page. And that's very surprising, considering V100 only had 2 pertinent numbers. V100, you just had to look at what the FP64 rate was and FP32 rate was, and the gem performance for int8, that's all that mattered. This one has a lot of gem acceleration, even for FP64 and other data formats, other new data formats, that there's too many numbers to go through. So it almost feels like there's 2 cards here, one for gem and one for everything else that is SIMT. So FP64 looks super impressive on paper at 19.5 teraflops, but then you realize that you got jebaited into thinking that was for SIMT. It's not for SIMT. SIMT is still 9.7, but hey, gem's there if you want to run HPL, So there's that. The other thing that grinds my gears a lot is that they did something really clever in terms of engineering. They took bfloat16's exponent and then combine that with the mantissa for FP16 within the gem units. They need to support both anyway, so why not make the number slightly wider by combining the best of both worlds, and maybe call that bfloat19, since it has 19 bits. But this is where awful marketing comes in and calls it TensorFloat32. I don't know where they got the 32 from. It's definitely misleading at best, and it grinds my gears. But the reason why they call it 32 is that you can natively run FP32 codes, mostly related to machine learning, and transparently accelerate them by discarding bits off of the mantissa. Not a fan, definitely not a fan, but oh well, this is what we get with machine learning, They also have structured sparsity acceleration. Why don't we go into that and dig at NVIDIA a little more? So this is what structured sparsity looks like for NVIDIA. Now, what they're essentially doing is taking a set of dense matrix weights and discarding half of them at every row and column. So you take a slice of one row with 4 columns in it, and then you discard 2 of them at random. Now, the more you think about it, the more you realize just how rigid this is in terms of the type of sparsity they're accelerating. First of all, it's only at best 50% sparse, which is in HPC world and not that sparse whatsoever. So it's very clearly targeted for something like neural network dropout, where you would be usually just setting dropout to 50% and calling it a day. So for that purpose, this works really well. But for any actual sparse workload, like sparse matrix vector multiply, I fail to see how this could be useful in any way whatsoever. Because I actually, if you attend the webinars that NVIDIA hosted during the GTC keynotes and stuff, you soon realize that this is not up to 50% or around at average 50%. This is strictly 50%. So if your matrix is 75% sparse and you cannot afford to have those rest of the 25% converted to zeros, you can't help it. You can't use this. You still have to default to the dense version based on SIMT. There's no way you can take advantage of this. This works for such a not narrow application area that it does grind my gears in that they're claiming sparse acceleration. This is sparse acceleration for a very specific application purpose, for a very specific data format that you can't really apply anywhere else. And that's why it like grinds my gears more, because this would be so cool to have. But oh well, this is what we get. I mean, I'm sure it's a stepping stone, of course. This is the first time they're doing it and it'll get better, but doesn't stop me from complaining for more. Now let's get into the SIMT performance, which is what actually matters to me if I wanted to port my code from a SemiRing gem to A100. Now there's some really cool new stuff, which is that you get asynchronous copies from global memory to shared memory. If you've done any CUDA programming, you would know that the first thing you do in terms of optimization is that you use shared memory. And A100 has new instructions to asynchronously load from global memory to shared memory. So you can overlap computation with communication. That's super cool. There's also barriers that are supported from the C++ abstract machine model point of view. So you can use stud barrier in your CUDA code now, which is also super cool. And what these two do together is that they allow you to set up gem pipelines that are deeper than just 2 levels. So you can have 3-level, 4-level gem. So you can software pipeline and hide the latencies of memory loads in the background as you do computation on your currently existing data. So this is super cool to see. It also adds new instructions that are loading. They're essentially strided load instructions in that you can specify a pointer to a 2D matrix or a tensor, and then load a chunk of that in the sense that you can load essentially a matrix like this. So if you imagine this to be in memory, you would normally load this as striped across all of your 32 warps, 32 lanes within the warp. So this load instruction for warp matrix multiply accumulate will essentially do that striping and stuff for you. So you don't have to issue individual loads. One single load instruction will load across the warp. And then there's also instructions for level 2 cache. Now, the really, really annoying part and super disappointing for me, I was actually pretty sad for 3 days straight, is that it actually is a regression for floating point 32 performance. It's a 7% regression in terms of performance per watt. If you just look at Volta versus A100, Volta is 15.7 teraflop versus A100 at 19.5. And although that is an upgrade, you are paying 100 more watts and definitely way more money. So yeah, the general purpose part of the GPU gets little to no love in terms of actual upgrade and value, like TCO value. Now, this does raise some pretty interesting questions as well. Like, what does this mean in terms of what the future of transistor scaling looks like for acceleration hardware? Like, the original reason for CUDA taking off was the fact that it was so programmable and that you could take advantage of an ASIC in a very programmable and flexible way. And this kind of seems to be robbing that flexibility away, in the sense that GPUs made sense because they were so much more efficient in terms of power, flop per watt and flop per byte, compared to CPUs. And if you have a regression like this, why would I use Ampere instead of Volta? Like, there's no reason for me to, especially for my workload. So where does this specialization really trend you towards? You know, there are some application domains that don't make sense on such a specialized version of the hardware. They might not make sense on A100s either. So you need ASICs, and no one's going to produce ASICs for extremely small application domains. So GPUs were a kind of a nice middle ground between CPUs and FPGAs until now for flop heavy computations. But with all these tensor cores being the center stage of the GPU, that seems to be going away as well, for better or for worse. I don't know if it's actually better, but hey, they better be sure about that, because this is definitely a regression for some of the workloads that you'd be interested in. This thread, I feel like, summarizes this point really well. This is a thread by Dan Ernst, who works at Cray, and that there's a lot of nuance when you're talking about performance metrics for something like the A100, because there's a lot of specialization that just goes beyond what GPU versus CPU would be, and that the GPU itself is made up of two different forms now. There's SIMT versus that you have your tensor core acceleration. And you kind of need to be a little more nuanced when you compare the performance and the generation on generation upgrade environment. So, oh well, yeah, there's that. You can find the links here, by the way, for all the sources. They'll be right next to the image if I'm linking them. Anyway, in terms of the overall package that you get from NVIDIA, you can also buy a DGX A100, which is 2 Rome hosts, no longer Intel, surprisingly enough. Although if you have kept up with the landscape, you would have seen this coming from miles away. Intel doesn't really have a PCIe 4.0 CPU right now. Even the future ones that have PCIe 4.0 have only half as many as AMD Rome does. So all that NVIDIA wants in this case is the bandwidth, because actually, if you look at what the acceleration hardware is, it's 8 A100s, each of which are 16 links. And then you have 8 Mellanox NICs, which are also by 16 PCIe 4.0. So even with 192 lanes of PCIe 4 from the 2 AMD CPUs, you still need PCIe 4.0 switches to satisfy all of the links. So it's a crazy bandwidth heavy machine. There's a lot of data moving around in this thing. Another thing to note is that these A100s are only 12.5% of them is fused off. So instead of 8 GPCs, you only have 7 GPCs. I believe there's a typo here as well. This should be 102 and not 112, but I'll make sure and double check on that. Yeah, it should be. I think it's fine. Whatever. We'll figure it out. Basically, you have 16 fewer SMs than the full version of the A100. You also have one-to-one GPU to NIC mapping, which means that there's no blocking on I/O. So any GPU that wants to perform an RDMA with any other GPU can do it at full bandwidth. So it continues the full bandwidth NVLink style non-blocking communication across different systems as well, and not just on the board. And of course, there's NVLink 3 on these systems, which are, I believe, 12 links of 50 gig SerDes. So 600 gig total. Yeah. SXM4 is 600 gig of signaling total. Analog seems to be taking a lot of power as well, actually. That's something I wanted to mention. If you look at the PCIe version, which has half as many NVLinks, the TDP goes down by 150 watts. And I talked to some people who know analog a lot more than I do, and they seem to think it's plausible that at least half of that TDP reduction, which is about 75 watts, comes from just the analog NVLink signaling part. So hey, that bandwidth doesn't come cheap.
So does that mean the perf per watt on the card might not look so bad?
On the PCI version, I expect it to look better, of course. But the PCI version also has some interesting caveats. They say up to 90% of the performance of the SXM4 card. Now, what does that mean? I mean, if you're going from 400 watts to 250 watts, you have to give up something in that it's probably going to be clock speeds. Oh, by the way, SIMT regressions, they actually come from a clock regression. So Pascal had a clock of around 1450, Volta had a clock of 1500 and something, and Ampere goes to low 1400s again. So they actually experienced a clock regression with this chip. And that's actually going to play a part later. I'm going to talk about that. There seem to be some very interesting engineering challenges involved with such a large die. Yeah, to answer your question, Elliot, I think for the PCI version at least, it's going to be super workload dependent. I think the SXM version will give you the peak performance no matter what you're running. But especially on the PCI version, I expect it to downclock a lot depending on, kind of like the Intel CPUs, in that if you're running AVX 512, they will downclock a lot because the power generation, heat generation is much higher. So the PCI version should be similar in that respect. But we'll find out. Like, I haven't gotten my hands on an A100 yet. I've been itching to, but oh well, they're kind of hard to find right now. And I'm sure I can't pay for one myself. I don't have kidneys left. Anyway, to get into some more lighthearted content, there's also a EGX A100, which is the edge inference pitch from NVIDIA. They basically took a ConnectX-6 card and slapped a A100 on it. So you can stick it in your data centers at the edge, do some smart NIC stuff so that the host never even sees the inference packets coming in. And you can just do your gem go burr on the NIC itself. That's cool. I mean, hey, when was the last time you saw a NIC with 400 watts of power consumption? Now you have one. So, go for it. Any guesses on how much this is going to cost? Probably 2 kidneys. But hey, it's cool. This is super cool. I wonder what you can do with these, because these also have a ARM host on the NIC itself. So can you do a completely hostless build? Like, I wonder if that's possible. I don't think so, but that'd be cool. Anyway, so a little more of the tech deep dive. This is something super interesting, which is, again, what I mentioned earlier. There's a clock regression with A100. And for a brief second, let's go back to the actual functional diagram of A100. So if I highlight something here, oops, sorry. I'm a mess. Can you guys still see my screen?
Yeah, I can still see it.
Okay. Hopefully this is better. Okay, yeah. If you actually look at this functional diagram, you have your 8 GPCs. The first one's here, second one, third one, fourth one. The L2 cache is actually split into 2 hubs. If you're familiar with the historic trend of NVIDIA GPUs, the L1 is the shared memory that you would normally use, and L2 is shared across the entire chip. This time around, the L2 is actually split into 2 parts. So let's explore that a little more. There's some really interesting things going on there. From a microarchitecture point of view, it's 40 megabytes total, so 20 each for one slice, and they're coherent with each other. So any data that you have in one, if you access from an SM that is talking to the other slice, it'll remain coherent, kind of like a CPU in that sense. The SMs will only use the local L2 slice, so there's a non-uniform cache architecture here, kind of like the AMD CPUs, where if you hit the local L3, you have a certain latency, but if you hit a remote L3, you'll have a different latency. Not only that, the memory controllers for the HBM stacks are striped across the they're homed on each half of the chip, but their interfaces are spliced across in a fashion where like 8 channels are mapped to different 8 slices of the L2 are mapped to each of the 5 HBM stacks. So this is also a NUMA architecture on a GPU. So if you access a certain part of global memory from one SM, that may not have the same latency as accessing another part of global memory. Now, you would care about a NUMA architecture on a single chip on CPUs, not on GPUs. I mean, GPUs are supposed to be super resistant to latencies anyway, and they have laughably bad latencies to begin with. So you would never really care about this. But the reason why I'm pointing this out is it's super interesting to see on a GPU for the first time. It's kind of interesting. You would usually only see on-package NUMA on the, for example, AMD Naples had an on-package NUMA architecture. Super interesting. The other side effect of having a L2 cache setup like this is that it's not actually 40 megabytes usable in the sense that if you're using the same data across the entire GPU, the coherence overhead means that you lose, it's not an additive capacity. The 50% of the residency is lost because the same data is being shared between the 2 L2 slices. So you need to kind of make sure that your data use across SMs doesn't have a lot of communication. If you're sharing a lot of data across all the SMs, again, the flop to byte better be high. That's essentially what it boils down to. There's also increased traffic and power due to coherence guarantees. And I think this is where the clock regression part actually comes from, in the sense that the die is massive. It's an 800 millimeter square die on 7 nanometer, which means that it takes light years for any signal to make it across the chip. And the timing, like, I don't envy the job of the physical design folks who worked on this chip, because it seems like hell to do timing closure on this. Like for VLSI folks, this is quite a challenge. So this, and the reason why I think that is, normally when you want to increase cache bandwidth, which is what they need to do to feed all of these extra CUDA cores, you would need to add more banks, and GPUs are very heavily banked in terms of SRAM anyway. But they had to split the L2 and increase the bandwidth that way, in a way adding more banks wouldn't have, because it would increase the complexity. Now you would have a cache that spans the entire 800 millimeter square chip. which is super hard to do in terms of the power costs that you would end up paying for the network on chip and the routing complexities you would face. So I believe that's the reason for going with that. The other reason why I'm also obsessing over the L2 is that you can kind of see where the next generation of NVIDIA GPUs will go. I have a very safe bet to know where the NVIDIA GPUs will head next, which is probably going to be a GPU that has 2 dies split across the middle with coherent L2 between them, and then more CUDA cores on each side. So you can kind of just like imagine slicing this GPU in half. That's probably what the next generation is going to be within the next 2 years. And I expect NVIDIA to ship the next generation fairly soon. The gap between Volta and Ampere was uncharacteristically long, 3 years. Usually it's 2 years. I expect them to be even shorter because they have a lot of competition. I mean, you can see where the effort went into making this chip, which is the gem part. And that's coming from the deep learning competition that NVIDIA has because there's so many startups. I mean, hell, I work at one. So there's a lot of competition for NVIDIA. So it's kind of easy to see where the things are going to head and what the future of GPU hardware looks like, at least from NVIDIA. So yeah, that's why I wanted to mention so much about L2. Hopefully you enjoyed the deep dive. But you know what? Who cares about nuance for microarchitecture anyway, right? You just have Gem, you run your deep learning workload on it, and you see Gem go burr, and that's that. Like, whatever. Who cares about CUDA? So yeah, whatever. Well, not so soon. Intel has also joined the chat in terms of Gem go burr. Sapphire Rapids, which is the server CPU that's going to be shipping after Ice Lake. And we'll talk about Ice Lake later, definitely. But Sapphire Rapids is the CPU that's going to ship with Aurora as well, which is the system we talked about last time, our Argonne National Labs exascale system. That's going to have a new instruction set extension called AMX, which is the 2D tile extension of your SIMD AVX extensions. It adds 8 more registers, which are called tile TMM 0 through 7. And each register is a massive 1 kilobyte each. 1 kilobyte register. Oh God, it's just junker. I don't expect this to be flip-flops. This will most likely be an SRAM based register, but still, it's kind of wild to think about how large the registers on the CPUs are getting. This cannot be small in terms of the die area cost for Sapphire Rapids for sure. The sad part is that it only supports matrix multiply accumulate for now, and only for int 8 and bfloat 16. So there's like a grand total of 12 instructions on the ISA manual for Sapphire Rapids, so whatever. The interesting part is that the instruction stream for this AMX is synchronous with the rest of the instruction stream of x86. So each core will have its own accelerator. So it kind of looks like if you remember x87 FPUs, it kind of looks like a coprocessor in that sense, in that like you can clearly see in the diagram, the IA host, the Intel architecture host, which is the main core itself, lives completely separate from this acceleration structure, which receives the commands over a shared bus. And the memory subsystem for the tiles are separate from the load store queues. Like if you think about it, the load store queues on Skylake X are 1 cache line each, which is just 64 bytes. So if you were to do a single tile register load, it would completely use the entire resources of the core. You would just completely choke everything else. So if you read the ISA manual for this, they actually have a dedicated interface with the memory controllers, which bypasses the normal memory semantics of the core, which is very interesting to see. But the instruction stream is still synchronous. And it can be co-issued with AVX and AVX 512, which is why I have this meme. Can you find the house fire on the slide? Imagine issuing AVX 512 and AMX instructions at the same time. I mean, Intel CPUs already downclocked by 600 megahertz and completely max out their TDP with AVX 512. So I wonder how this will go down in terms of power consumption. That should be interesting. But wait, there's also player 3. Intel has bought Habana Labs. Habana, I haven't covered Habana before, but they're also a Gemgo Burr company. They're trying to accelerate machine learning, and Intel has bought them. Now, this should be a super curious decision to you, and I'm replaying my train of thought when I actually heard this news first, because in Q2 roundup of 2019, we covered Nirvana pretty extensively. Like Nirvana had their training ASIC as well as an inference ASIC that Facebook was going to use. OCP also had developed some hardware for these gumstick-like inference accelerators. You can refer to the previous slides if you like. And I spent so much effort of my life covering Nirvana. And then Intel goes ahead and buys Habana. I'm like, why would you buy two companies that are literally solving the same problem with very similar hardware? And at the time, I had predicted that Nirvana would be killed off and Naveen Rao would leave. And guess what? Uh, Intel shut down Nirvana. AIPG was formed at Intel after they had acquired Nirvana in 2016, and now it's no more. AIPG's lead, Naveen Rao, has also left Intel. NNPT, which is what I spent most of my time covering last time, will no longer ship ever to any customers. And NNPI will only ship to existing customers, of which I only know of one, which is Facebook. So I don't know what Intel is going for here. If you think about their macro level strategy, they have so many accelerators that are all trying to solve similar issues, which is that GEM needs to be accelerated. And which one do you use if you're an Intel customer? Do you go for NNPI? Do you go for Habana Gaudi or Goya, whichever one is the inference one? Do you go for their new GPUs that are supposed to launch sometime this year? Do you go for the AMX on Sapphire Rapid CPUs? Do you go for VNNI on Cascade Lake? There's so many things to choose from. Like Intel, make up your mind. What is going on? So confusing. But and yeah, another machine learning accelerator, or supposedly a GEM Go-Burr machine from Intel. When we talked about Aurora, we didn't know what kind of GPU it would have. Well, at SC19, they disclosed Ponte Vecchio. Oh, I hope that's how it's pronounced, Ponte Vecchio. Ponte Vecchio. But it's the GPU that Aurora will ship with, and it's going to be a 3D stacked multi-chip GPU with something they called Rambo Cache, which is perhaps the most cringe technical marketing I've ever come across. Essentially, what Rambo Cache is, and I kid you not, this is what Raja Kuduri said on stage during their keynote at SC19, and I had my mouth dropped to the floor, but it's a 1 gigabyte or so-ish last level cache that the GPUs can share between the chiplets. And it's going to be coherent with the host as well through CXL. So CXL is the interconnect that we covered last time. So it's a very cool, neat little chip. The configuration that the Aurora will ship in is 2 SPR CPUs, which is Sapphire Rapids with AMX, and 6 Ponte Vecchio GPUs. The programming model is, of course, one API, which is what Intel has been talking about for a long time, which is essentially just SYCL with Intel extensions. Big fan of that. And the real question over here is, will this even ship? We're going to go into the 7 nanometer issues that Intel is having sometime later in the presentation, but will this ship? Like, this is supposed to be on Intel 7 nanometer. And apparently they're also going to use TSMC for this thing. But what's going to happen to this, Like, no one knows. There's also supposed to be Arctic Sound, which is the GPU leading up to Ponte Vecchio. It was supposed to launch sometime this year, but there's been no word from them. At GTC, they were also supposed to launch a white paper detailing the microarchitecture of the Arctic Sound HPC GPU. That has also not come out. So I don't know what's happening at Intel. I hope they don't slip on their DOE roadmaps, because that would be pretty bad. If you remember, the Aurora system was originally A18 at Argonne, which was supposed to be the KNL successor, Knight's Mill. And that got delayed because Knight's Mill died, because 10 nanometer never shipped. Now, if 7 nanometer doesn't ship and Ponte Vecchio doesn't ship as a result, like, does that mean or A21 also gets delayed? Like, that's scary to think about. So good luck DOE, and good luck Intel, pour one out for you.
Was Blue Waters the most challenged system before Aurora?
Before my time, I'm not aware. Okay. Maybe Jeff knows if he's here, or Rich.
I'm just curious how precedented is it to push a leadership system 3 years?
Yeah, I mean, I actually don't know. I mean, it's definitely not a good ideal thing at all. I mean, if you think about it, the architecture completely changed. The KNL codes would have run without any porting efforts on KNH. So now they have to rewrite every single code for KNL to some other acceleration or like programming model. So it's a pretty big deal already anyway. You have to rewrite every single HPC app that you ever ran on Cori. So it's bad enough already, like, it can't get worse than this, other than the $500 million that DOE has tied up in the Aurora contract. So who knows, The other issue is that the prime contractor for Aurora is not Cray. So they can't just switch out the GPU and go for NVIDIA or AMD. The prime for the contract is actually Intel. So it's not as simple as renegotiating or going for some other accelerator, because the Intel is the entity they need to talk to. And you can imagine how enthusiastic Intel is about using NVIDIA or AMD GPUs on their machine, So yeah, it's a mess. I don't know what Argonne's going to do. I wouldn't be too I would be shocked, but I wouldn't be too shocked. Like I would basically have a surprise Pikachu face if DOE ditches Intel and goes with someone else if it doesn't ship by 2022. I also don't think Aurora will ship in 2021. Like they were supposed to ship in late 21, which is what I said last time. I don't think that's happening. It may happen, who knows, but I don't think it will. Anyway, let's go to more gem memes. This is the new GraphCore Colossus chip. We had covered the original version of GraphCore a very long time ago. This is basically a 7-nanometer shrink of the same chip. It's very expected. The only new thing that I saw and I didn't expect was the DDR4 interface. So to give you some context, the GraphCore ML chip is it's a large monolithic die like NVIDIA would make, but it doesn't have any external memory whatsoever. So all you have is the 300 megabytes of on-chip SRAM. So if you have seen the new trends in ML, which is these GPT and BERT models, they're 700 billion parameters or something crazy like that, which is not something you can even fit with a cluster of GraphCore chips. It's just simply not possible, even if you had thousands of the GraphCore chips. So what they've done is they've added, in addition to the tripling of the SRAM on chip, they've added DDR4 interfaces to offload and give them more breathing room in terms of the parameter sizes on the new neural network models. I feel like that's a very smart move, personally speaking, without my Cerebras hat on. Please don't associate my comment with that. But this is a smart move. This is cool. And it will definitely help them with adoption. Their software stack also seems to be maturing. There's a white paper by Citadel now, who's one of their customers, publicly stated. And there's a good dissection of the performance characteristics and micro-benchmarking of the GraphCore chip. If you've seen the NVIDIA Volta and Turing microarchitecture analysis, it's the same folks who've worked on it. They also have a custom interconnect architecture, just like every GEM chip does, which is that they have a 3D ring fabric. The ring fabric here is very interesting. Usually you go for like a tree or an alt-wall connected fabric, but they've gone for a ring instead, because usually neural networks are sequential layers of computation. So what they're hoping to do here is that you map one layer or to each node or each accelerator, and then just ring broadcast to the next layer for your next, like a pipeline fashion for training, model parallel training. Their programming model is what the most interesting thing is, and I encourage you to read more. I can't go too much into detail here. It's very wacky, and I've never used it myself. But on an NVIDIA GPU, you would be doing, or any other accelerator, you'd be doing your fabric communication at the same time as your computation. In fact, like the asynchronous copies and loads and stuff encourages that even more. Whereas what GraphCore is doing is something called a bulk synchronous programming model, in that you do the computation in the SIMD lanes first, and then all computation stops, and then you do an all-to-all communication phase across the fabric as well as on-chip. So I've heard from people who actually program this that it's kind of annoying, in the sense that it's not that it's bad or doesn't work. It's very unconventional, and you have to like retrain your thinking to fit the new chip. So there's that. There's also a comparison slide. I don't know how much this means. Like, I can guarantee you this slide doesn't mean anything in terms of the performance. You can't look at peak performance and claim that we're better. Like, so whatever, this is a meme slide. It doesn't mean anything. The interesting part is that you have the price listed here. So you can know what a ML chip actually costs to buy, which is actually not that expensive. I mean, depends on what you're trying to do with it, but yeah. Anyway, so to more lighter news, this is also something that we saw coming, and I think I talked about last time. Last time we talked a lot about RDNA and the GPU latency improvements that AMD made. So they've come out and said that CDNA is going to be a different architecture now. So the gaming GPUs and the compute GPUs from AMD will be 2 separate lines, 2 separate microarchitectures. The ISA is also different, interestingly enough. So GFX 900 series are the CDNA ISAs now, which is based on the original GCN ISA. and the RDNA gets a 1000 ISA designation within the LLVM compilers and stuff. I was looking at some commits on the LLVM backends, and there seem to be some matrix multiplication, like gem acceleration instructions as well. So I'm sure the next generation of MI100, I think it's called, will also come with gem pipes, probably. They should also move to MCM, I would presume. Whatever, I don't know if MI100 will be, but it's very clearly the direction that GPUs are going in as well, in that they're no longer going to be a single monolithic die. They've also said Milan will be shipping this year. Now, I didn't have a meme from AMD, but AMD marketing doesn't disappoint with the cringe. Don't get mad, get AMD. Oh God, just don't do that. You know, don't market with this. It's not a good strategy. Another exciting news, DDR5 is coming. So DDR4 has been around since 2014. And all that DDR5 is really doing is that it's increasing the effective bandwidth. One of the major issues with DDR4 was that the refresh would lock up the entire rank, which is the entire DIMM if you have a normal desktop chip. So instead, this chip is dividing stuff into 8 bank groups, and you only need to lock 1 bank group at a time of refresh. So you can still use the other 87.5% of the DDR and keep accessing data. The burst length is also double now, which increases your effective utilizable bandwidth. You can also access more random data because the 64-bit channel has now been split into 2 32-bit channels. The extra 8-bit are for error correction. And the data rates are super impressive. So DDR4 capped out at 3200. This one goes up to 6400 megatransfers. 6,400 megatransfers per second. There's a really nice Micron write-up there's a really nice Micron write-up that goes into what went behind increasing the data rate, and I don't understand the analog stuff, but it's super cool. And surprisingly, it's also lower power. It takes up, I think, like 15% less power than DDR4, which is cool to see. So essentially, with everything else being equal, including frequency and whatever, the new banking strategies and refresh rates and burst length give you 36% higher bandwidth. And with the higher data rates, you get a 122% cumulative increase in bandwidth. So that's awesome to see. Not that the more bandwidth will ever be enough, but hey, it's a good step in the right direction. Let's also talk about ARM. Last time I talked about the ARM A77 cores, which is DMOS. This year they've released Hercules cores, which is a refinement of A77. It's not as big of a deal as DMOS was. So DMOS went from 8-wide core to a 12-wide core. This one is still 12-wide, but it's a refinement in terms of the power, performance, and area. It's also targeted for N7, but actually has a smaller area with higher performance. So that's cool to see. The performance is also higher given the same power, everything else that you would expect. And at ISO process, ISO every frequency, it's a 7% IPC improvement. The way they've done this is they've added more front-end optimizations like fused instructions, more of them, a new renaming algorithm, new prefetch patterns, cache optimizations. Cache sizes are also adjusted as far as I know. And on the back end, they have added 1 more multiply unit and 1 more AGU. The really interesting thing here is that they've doubled the store bandwidth. So you can now do 32 bytes per clock instead of just 16. So that's cool to see. Now, this 7% IPC, if it's too low for you, they also have a off roadmap core called Hera, which is essentially the same core, but with 30% higher performance. So this is like the pedal to the metal version of the A78. And this one gives you the 30% single thread improvement over A77. The notable differences is that it has a lot larger reorder buffer. It's actually the same size as Skylake X or Zen 2. So ARM is really catching up here. It's super impressive to see. It also has the fastest renamer in the industry. So I think Zen 2 does 6 renames per cycle and Skylake X does 5. This one does 8 renames of registers per cycle, which is also super cool. Decode is up, dispatch is up, massive micro-op cache, which is the cache for decoded instructions, larger than Sunny Cove, in fact, which is the Ice Lake CPU core, if you remember. And it also has the same floating point performance as Zen 2 or Skylake client, Skylake S, not the X. And of course, larger branch target buffers and everything else that comes with a beefier core, essentially. So this looks Haswell or higher than Haswell performance. So Intel, beware. This is kind of a diagram version of what the differences are. You can go into this later if you would like. What are the notable ARM SoCs coming out this year? Well, there's a lot of things. Thunder X3 finally revealed their details, which is 96 cores, SMT4. We had talked about this before, but the core count wasn't official, I think. Ampere also has their second generation SoCs, which are 80 Neoverse cores. So mind you, Neoverse N1 here is actually the RS core, which is 2 generations behind A78. So the Hera and Hercules are A78. These N1 cores are actually A76. So the implementation of ARM cores usually lags behind by 2 years. They have the same number of PCIe lanes as AMD Rome does, so that's also super cool. But they also support C6. C6 is the coherent attached standard for host and device coherence. Our AWS is also shipping the SoC. Well, shipping is a generous term in this case, but they're using N1 based cores for their Graviton 2, which is the 64 core SoC. The really big news this quarter are that Apple has ditched Intel completely starting this fall. It wasn't as much of a shocker, to be honest. There's been rumors of Apple switching to in-house silicon for the longest amount of time now, and it makes complete sense for what they're trying to do. They're trying to drum up performance as the reason, and yes, I expect the performance to be higher, but let's not kid ourselves. They're a publicly traded company. This is a margin play, so yes, it's going to give you more performance, but at the end of the day, they're trying to make money. Nuvia also came out and said that they're actually making ARM chips. So I don't think we've talked about Nuvia before, but if you've ever seen John Masters on Twitter, he actually lives right next to MIT. Great guy. They've been talking a lot about their chips and how high performance they're going to be. So they're going for a super high performance server class, single thread optimized ARM chip. And supposedly they have something really cool cooking in the pipe. So it'll be interesting to see once they actually start talking publicly. But yeah, none of these are major surprises. Like they're supposed to be big surprises like Apple ditches Intel, but at the end of the day, surprise Pikachu face. Intel Cooper Lake is also shipping, which is literally the same as Skylake SP. So it's the third version of Skylake, which is why I have new folder 3 here. Same core with bfloat 16 support added to AVX512. Now, shipping is also kind of a generous term. I can't see anyone like Dell or HP actually shipping this to you, so you can't just go ahead and buy this. It's on a new platform called Whitley, which is supposed to be shared with Ice Lake, but Ice Lake has also not shipped yet. They say Ice Lake is ramping, but if you remember, a year ago, I said Ice Lake is ramping as well. So deja vu there. You can kind of put the 2 and 2 together to figure out what's going on. The 8-socket version is shipping to Facebook, or was it the 4-socket version? I think Facebook is the only one using Cooper Lake for now, publicly at least. I don't know if anyone else is. Nothing burger really. Ice Lake also has caused a roadmap shift for Intel in that Sapphire Rapids is probably going to be towards the later half of 21. If not, I don't think it's going to be 21 either. I think it's going to be 22. But Ice Lake is also later now. It was supposed to be 2018. Oh, wait, it was supposed to be 2019. Oh, wait, now it's turning 20. So it's like 2 years late now because of 10 nanometer. And I think it's supposed to have 30-ish cores. I don't know, though. But I've heard that the TDPs don't look good either. The Sapphire Rapids part is the one that's going to have AMX. And then Granite Rapids is supposed to be on 7 nanometer, but who knows what's going to happen to 7 nanometer now. So let's see. We'll see. I have a lot of things that I did not have the time to cover, some of which is super cool stuff in that MLPerf's latest round came out. Actually, the last time it presented was the first time MLPerf had actually ever released results. So I covered in the last roundup MLPerf 0.1. Right now, it's the 7th round of MLPerf, and NVIDIA and Google are crushing it, as one would expect. They were back then too. So TPU v4 is not something they've ever talked about before, but they showed results for it. People seem to be impressed, but actually, I did some napkin math. It's literally what one would expect if you go from 16 nanometer to 7 nanometer. They probably just shrunk the die down and added some more cores. You know, that's essentially what every gem accelerator company is doing. I mean, you get a new node from TSMC, you slap some more SRAM onto it, you shrink the logic, and you add more cores. That's literally what everyone does. So they also did that, I'm assuming. The Blue Gene Q core has been open sourced, by the way. So this is a part of the Open Power Initiative. IBM has made the Power ISA open, which is something I talked about last time. And the RTL for Blue Gene Q is now open source. So if you would like to play around with FPGAs or develop your own core, have at it. I've also covered the NEC vector engine before. They had a small refresh. They're now using Flashbolt from Samsung, which is the higher bandwidth memory. So they're doing that. I have also covered Xilinx Versal before, which is the literally kitchen sink FPGA. It has everything. The premium series adds a gold-plated kitchen sink to its portfolio, and also offers you 800 gig Ethernet, which, like, come on, where have you even seen 400 gig Ethernet deployed before? They're doing 800 gig Ethernet here. Intel also shipped Lakefield, which is a big little core, big little chip based on x86. It's kind of a meme. I'm super bummed about it in the sense that the big core actually has AVX512, but they fused it off for ISA parity, which kind of kills the whole point. Oh well, whatever. There's a really cool joint research work by IR Labs as well. So I've covered IR Labs before for their silicon photonics stuff, but they're actually starting to ship a FPGA, this one over here, which actually has silicon photonics links on the FPGA package itself. Super cool to see. And this should allow for like some insane signal transferring rates between chips on the same data center. OCP also has a new chiplet architecture, which is open source. So if you've noticed, a lot of the chips are being broken down from being monolithic to smaller dies as transistor scaling becomes harder and harder and monolithic dies get more expensive. So what OCP has done here is that you can envision a future where Xilinx is the one developing the FPGA, but then you can take that FPGA chiplet and put it on an AMD CPU or something, even though they're two different companies developing two different roadmaps. So this is what the OCP ODSA is for. You can combine and mix and match chiplets and make your own SoC perhaps in the future when scaling gives you more flexibility. Like imagine the possibilities of heterogeneous computing in the future where you can have everything, including an FPGA, silicon photonics, and a GPU on the same chiplet, on the same 3D packed package with the CPU host on the same package too. That'd be super cool to see.
Is this the first time that OCP has dived into a chip? I've missed this.
So this is not a chip. It's a standard for connecting chips together.
So I guess have their specifications ever dived into the chip? It seemed like before it was rack level, server level. Okay.
Yeah, exactly. So this is the first time they're actually going into the level 0 interface at the hardware, if you will, like a physical link layer, if you're talking about the OSI model in a way. Now, for absolute, if you just want to laugh at a HPC announcement, this very morning, which is why I didn't have the time to make this, Tachyon showed off their performance for Prodigy, and it's a VLIW chip, 4 wide, and they're saying that they'll have higher performance than x86, ARM, and RISC-V's native cores, translated to VLIW by their Magic compiler in real time with a smaller core area, higher bandwidth, and just as high of an AI performance as an NVIDIA GPU. Like the claims that these people are making are something like, you got to be smoking something special to make claims like these. Like I wish them luck with their Magic VLIW compiler, but Itanic is still pretty fresh in the memories of people. So let's see how that goes. I wish them luck. I encourage you to check out Tachyon. They're doing some crazy stuff. Positive or negative, that's for you to decide, but it seems completely bonkers to me. By the way, to give you an idea of what the FPGA chiplets look like, you can kind of see it over here. We actually talked about this last time, if you remember, and I still can't ignore this one. Like, come on, it looks so funny. Anyway. Okay, now we're finally going to HPC systems. Fugaku, of course, is the talk of the town these days. We've covered A64FX before, which is the ARM HPC CPU. But they have published some excellent documentation. Fujitsu has documentation up on GitHub about the reorder buffer sizes, which SIMD lanes are issued on which pipes of the floating point unit, how many instructions can be issued to this. There's so much detail you can find here, and it's amazing to see. I'm so happy. It's stuff like what you would normally have to reverse engineer Intel chips for, that's available in the public documentation. It's super cool. They also have a really strange interconnect topology for Fugaku. So it's not, so like we covered Shasta last time, which is using Dragonfly everywhere. This one is a 6D torus, where 3 of the dimensions are extended in the sense that, and 3 are compact. So if I say compact, the extended ones should make sense. The compact ones are 2 by 3 by 2 only. And essentially what you do is you make a 3D torus out of these 2x3x2 cubes, and then lay them out that way. I was wondering how MPI rank mapping would be done to this, which is super cool. But again, Fujitsu documentation saves the day here. They have a way to embed a 3D hypercube. Sorry, I think it's a 3D torus that they're trying to, yeah, same thing, I guess. And they're trying to embed that into the 6D. So they have an algorithm that does that for you. What should be really cool is that there should be some algorithms that use clever ways to map their problems onto a 6D phase, a six-dimensional MPI rank. So that'd be cool. That'd be cool to see. But they have the top 500 spot for now, like the top one spot on top 500 for both HPL and HPCG. Talking about flops per byte though, Fugaku also takes the cake there. Their HPCG achieves 3.2% of the peak floating point performance, which is amazing. 3.2 hasn't been seen in a long time for any of the GPU systems. To give you some context, Summit gets only 1.97. Only is also, it's a really good result, but to give you, to rant on A100 a little more, Summit is V100s on which the HPCG is running. A100 based Selene, which is number 7 on top 500 now by NVIDIA, is only getting 1.87. So again, in terms of flop per byte, A100 is actually a regression over V100. I will keep harping on that. A100 is not a straight upgrade as people may imagine. So something interesting to note. El Capitan was also announced. Totally didn't see this one coming. Another surprise Pikachu face, but who would have thought that Summit and Sierra would continue their sister system legacy to Frontier and El Capitan as well. So essentially it's the same system as Frontier, which would be at Oak Ridge, and this is the Livermore sister system. It's going to be slightly larger actually, at 2 exaflops. So Summit is the larger one between Summit and Sierra, but in this case, El Capitan is the larger one. And it's going to be delivered a year later with the same amount of money. So that's also really cool to see. Same amount of money, but you get, within a year, you get 33% more performance. Amazing. It's also a full AMD system, which is going to be a Genoa-based CPU. So Genoa is the one coming out of Milan, and Milan is the one launching at the end of this year. So that should be around 21, 22 as well. And then the 23 system is the semi-custom version. And then it's going to have a 1-to-4 host-to-device mapping. They also have fully coherent CXL links between the CPU and the GPU. In this case, it's not CXL, it's Infinity Fabric, but essentially the same thing. And again, Cray Shasta is everywhere. Cray's done a fantastic job this time around, it seems. Other software and systems as well. So there's 2 other notable systems I would like to talk about. This is a very unique system. Speaking of Gem Gober, the Pittsburgh Supercomputing Center has a new $5 million system called Neocortex. And that's going to have 2 Cerebras CS1s as the main compute devices with 1 HPE system as their data store. They're also going to have, University of Florida also has a AI supercomputer, which is 148 DGXs. Makes a lot of sense if you're just making an AI supercomputer. And the thing I would like to take a dig at for C++ is that Fortran now has a freaking package manager. Fortran has a package manager. C++, please just, it's frustrating. Oh yeah, and speaking of Cray is now part of HPE, which I guess a lot of people have mixed feelings about. Shasta was also rebranded to HPE Cray X. Now the X is supposed to stand for exascale, but I can assure you, whenever I search for Cray X, I just get results for Crazy X, which is somewhat unfortunate SEO for HPE, but oh well, they have to deal with that now. And let's go and quickly wrap this up with some silicon fabrication news, as I usually do. TSMC is, as always, knocking it out of the park. They're doing amazing. N5 is in production for iPhone, for better or for worse. iPhone always ships with the latest node. So as much as us HPC folks would like to have one, Apple has all of them booked. So N5 is in production right now for whatever the next iPhone is, I guess iPhone 12. And also, I guess, the ARM Max at this point. N3 is also just delayed by 1 quarter. I hope this is not Intel terminology 1 quarter, because in that case, it would be like a year. But TSMC seems to be doing fine. And they're also building a fab in Arizona. Now, this is the discussion we had a year ago in person when I said we should not record this. At the time, we had talked about Taiwan's proximity to China and how it could be a contentious issue if TSMC ends up becoming the dominant fabrication provider. Seems like they're getting a lot of money given to them to develop something in the US so that you can preserve the manufacturing edge here in the US as well. So I hate to say I called it, but this was coming for a while, and it's very scary to see. And we're going to go into it later as well. Samsung seems to be not doing too hot. We talked about the 7-nanometer process last time, but Power 10 is late. Power 10 was supposed to ship earlier from what I've heard, but they're only holding their hot chips keynote within the next 2 weeks. So there seems, and there's no new updates, which is never a good thing from a fabrication facility. Like, yeah, they seem to be slightly slipping as well. I hope they're not, but it seems like they are. And that's also very scary to see because TSMC is the only one left at this point. Intel is just bro moment on bro moment. We're gonna go over it. Yeah, but this rings true. I don't know if you guys remember me playing one of these. I won't play one right now for the interest of time, but I encourage you to look at these meme videos about Intel 10 nanometer. They're pretty good. NVIDIA is also apparently looking to buy ARM. I don't want to spend a lot of time on this, but it doesn't sound credible to me. It sounds crazy. Even the ARM co-founder thinks it's crazy, so whatever. Okay, now we're gonna go into the parts that I would usually not have recorded. So Elliot, it's up to you, but there's some really scary developments in ARM land in the sense that ARM China has kind of gone rogue. So ARM has a joint venture with a Chinese investment company where the investment company holds 51% of the share in China, and they can operate in China that way. But they originally fired the ARM China CEO at the beginning of June over the fact that he started fundraising for ARM China without approval from the main ARM UK branch, and then he refused to step down once the board fired him. Now, this is bad in the way that I don't have words to describe how bad it is, because what's happening is that he is refusing to step down and trying to rally the ARM China employees to stick by his side, while ARM UK is saying that they're spreading fear, uncertainty, and doubt in the Chinese employees. This is a quote from the actual Bloomberg article, in that Wu has hired personal security and won't let any of the representatives of ARM Limited on the board on the premises. Like, it's crazy. Like, what is going on? Is this South Park? ARM China also said to Bloomberg that things are fine. But they're also saying in their statement that they have the exclusive rights over IP from ARM in China, which includes every latest Hercules or Heracore, I'm assuming, I don't know for sure. But like, ARM's entire business model is based on selling IP. And if ARM China has gone rogue and has IP control over everything, and China wouldn't enforce that IP rights, then this is bad to the degree of, like, semiconductor lawyers are super scary in the first place. They're hounds. And this doesn't seem fun for anyone involved. This is awful, 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 awful. So I don't know how this will unfold. Yeah, this is still developing as we speak. So we'll keep an eye on it.
This news isn't coming solely from Bloomberg, is it? Because I know they've had some run-ins. Okay.
No, these are official statements made by ARM and ARM China. There's a lot of communication from the parent companies themselves and their statements issued. But ImageTech also is like, if you remember Imagination Technologies, they're the first ones to ever ship ray tracing in a GPU chip, and they were the silicon house for Apple's GPUs before Apple stopped using them. They also have a similar thing going on right now, where their board got overtaken by the Chinese joint venture, and that they're now also doing a joint venture. So there's a lot of talk in the UK political sphere about Chinese joint ventures going for UK semiconductor IP. So there's a broader picture here that I'm hinting at, but I would encourage you to do your own research. I'm definitely not coming to any conclusions myself yet, but it's scary to see. And together with Intel's manufacturing stuff and TSMC becoming the only dominant manufacturing place, there's a lot of nationalistic tension, if you will, building up. I mean, TSMC is making a fab in US, which is what they would never do. TSMC has publicly stated that they're only making a fab in Arizona because they're getting government grants to do so in the first place. And Intel has also delayed 7-nanometer by 6 to 12 months. So the only company left on the planet right now making leading edge chips is TSMC, which is in Taiwan. And I mean, the geopolitical aspects of this do not look favorable for anyone, not for China, not for US, because China, HiSilicon, which is the largest, one of the largest customers for TSMC, the entity rule passed by US basically forbids HiSilicon from using TSMC at all. So the Chinese semiconductor market doesn't have access to leading edge IP anymore. And in the 21st century, if you can't make chips, you can't do anything. So you can imagine the kind of geopolitical tensions this would be raising. I mean, there's also the other fact from a business point of view that we're going from one monopoly, which was Intel, to another monopoly, which is TSMC now. So like, and this is a much worse monopoly to have because it controls everything within the semiconductor sphere. So where do you go? Like, you need to make chips at some point. Like, if you can't make chips, you can't do anything. And a monopoly at the lowest rung of the ladder, if you will, is the worst place to have one. So it's scary from many sides. Like, there's a lot of talk about bringing semiconductor manufacturing back to the US. And with the rising tensions of like all of the things that are happening right now, it seems fairly scary. I would encourage you to do some more digging here with the HiSilicon story as well. There's a lot of scary things going on, but it's something I wanted to highlight because I feel like even though we talk about HPC hardware and software and stuff, this is the kind of stuff that can have a very long-term impact over the next decade or two. So it's just something I wanted to highlight. You can reach your own conclusions if you will.
Thank you.
But
it is long-term though, right? Like that fab in Arizona, when does that go online? 5 years,
I
10
believe
years?
it's 23, no, 20,
Oh, okay.
very soon,
Okay.
yeah. But it's not the leading edge. So by 23, TSMC should be shipping 3 nanometer. But instead, this 23 fab, which is going to go online in 23, is going to be N5. So one node behind.
Yeah.
Yeah.
Okay. Well, thank you, Vijay.
Well,
I think
yeah.
we'll stop the recording here and see if other people have comments and we can chat. For all you people watching on YouTube, hope you enjoyed and I hope you can join us in person next time.